All right. Welcome. Today, we'll continue talking about convex optimization as a tool for design of algorithms. So let me reshare. So, right. So, what's the plan? So the plan is first we will finish the proof of gradient descent from last time. We didn't really do a proof. And then maybe the couple of small remarks, and then we'll start talking about mirror descent. Okay, so let's go back to our algorithm that we had discussed last time, which is the gradient descent algorithm. Okay, so just to recall, this is the algorithm we have. We have a convex function f. It's L Lipschitz, meaning for every pair of points x and y, well, I guess the way we will use it is the gradient of f of x is always at most L in norm, just a bound on the how quickly the function changes. And our iteration is clearly the following. It's just xt plus 1 is xt minus eta times the gradient. Okay, so what's the theorem we want to prove about it? So the theorem that we want to prove about it is the following. So you want to claim that after t iterations, okay, after t iterations, if I look at the average value of the function on my iterates, it's not much larger than the optimum value. So this is the optimum value of the function, the minimum value of the function. This is min x f of x, and let's say that this is at most square root t, where r is the distance from our original point and the optimum. So if you start at a distance r from the optimum, and you run for t iterations, your difference between the average value of the function and the optimum is at most RL over t. Okay, so what's the proof? Well, the proof is going to be short, but let me just do it carefully because it's sort of, the same kind of schema or proof schema will appear again and again. So, all right, so right, let me write down the first xt times xt minus x star. Okay, so where is this coming from? Well, this is coming from the definition of convexity for a convex function. If you recall, f of y is always at least f of x plus the gradient of f of x times y minus x. Okay, so this is, the function is always above the linear approximation. So if this is x, the linear approximation to the function is this, and the function is always above the linear approximation. Okay, and a consequence of this is, if you just invert it, another way to, flip this statement around is, if you're anywhere, somewhere, let's say you're here, right? Your xt is here, okay? And your x star is somewhere here, okay? Now, another way to say this is, you want to say that the gradient of at xt is steep, at least as steep. Well, how steep is it? Well, the claim is that the gradient at xt is steeper than this line that joins xt and x star, right? Is steeper than line joining xt and x star. So, I mean, in one dimension, of course, you have the multidimensional version of this, but basically, what is the line joining xt and x star? How steep is that? Well, that is f of xt minus f of x star divided by xt minus x star. Okay, in some sense, this is the reason why you're never actually lost in a convex function. If you have a smooth convex function, wherever you are, it doesn't matter where you're in the domain. If you look towards x star, which is the lowest point, along that direction, the gradient or the gradient will be very steep along that direction. If you just look towards x star, no matter how complicated where you are. So that's what this is, and that's our first step. That we're just saying the gradient is at least this f of xt minus f of x star. Okay, so this is good. Now, now what do? I'm going to just substitute for the gradient from my update rule. I'm going to write this as x t plus 1. Sorry, I had to say xt minus xt plus 1 over eta inner product xt minus x star. Okay, I write my fonts on x are confused. Like there's some are different, but all of them are the same x. Right? So it's just xt minus xt plus 1 divided by eta times. So this is just by definition of gradient descent. This is from the update rule. Right. Okay, so far so good. And now we'll forget about the eta for a moment, and we will use this other fact. I'll write it on a separate page because we'll be using this in a different form again. It's just a silly identity, but it has a name because law of cosine. I think it's the law of cosine. Okay, so what is it? Well, it's just this simple fact. So let me get this right. Okay, let me just write it and see. Okay, so it's this, why is it called the law of cosine? It's just an identity you can expand out and verify. Well, why is it called the law of cosine? You know, if you remember from plane geometry, if this is A, this is B, this is C, I guess let me use different letters, not to confuse it. So if this is X, this is Y, this is Z, then, you know, Z squared is equal to X squared plus Y squared. I want to say plus 2xy cosine of the angle theta between them. Right, this is in terms of vectors, you could say it's norm x squared plus norm y squared plus 2 inner product x comma y. Yes, okay, thanks for the correction. It's minus 2xy cosine theta. Yeah, thanks. Okay, so this is basically that, if you call this point A, this point B, this point C, A minus C is this vector, B minus C is this vector, and A minus B is this vector. So it's just that. Okay, so and the way to verify it is, the proof of this is just expand out the RHS, and it will turn out to be equal to LHS. Okay, it's just really easy. So I'm going to apply the law of cosine here. And expand out. Okay. So I'll keep the eta outside. What I'll end up with, I'll get a 2 because of the law of cosine. So I'll have xt minus xt plus 1 whole squared plus xt minus x star whole squared minus the difference between the two, which is xt plus 1 minus x star whole squared. Okay, so that is okay, just apply the law of cosine. Okay, so now this is good, because if you look at this expression, there is a telescoping happening here. So what do I mean? I'll just rewrite this whole expression again in the next page. Okay, so I have f of xt minus f of x star. This is less than I keep the 1 over eta out. I get x t plus 1 minus xt whole squared plus xt minus x star whole squared minus x t plus 1 minus x star whole squared. Okay, that's the expression we have. All right, so what's happening here? The second term here, you see that it's a difference of t and t plus 1. It's like d sub t minus d sub t plus 1. That's the second term. It's a difference of two distances, right? Whereas the first term is, of course, is just the length of the step you took. Right, the first term is the length of step you took, second term difference. Well, the good thing about these differences like this is that if I add it up over different values of t, they telescope. So meaning, if I take this inequality and I add it up over all values of t I equal to 1 through t, if I sum this over all values of I equal to 1 through t, okay, what do I end up with? Well, I'll have f of xt minus f of x star, I guess. That's fine. Is less than or equal to, well, the first term, you can't do anything. You're just going to add it up over all values of x, I equal to 1 through t. So it's just the, I guess the first term is sum of squares of how much you move, right, in each step. Okay, I'm going to keep it that way. The second term is nice, right? The second term, something nice happened there. Well, it was a difference of t and t plus 1. So when you add it up over all t from I equal to 1 through t, things neatly cancel out. And what you end up with is just the first term. Right, so this is, I just got this by adding up over all t.
Professor, what's I over here?
Oh, I'm sorry. Thanks. I should say f of xi minus x star. Yeah, yeah, let me just change that to t. Let me do t. Okay. Yeah, let me add up overall I equal to 130. Thanks. Yeah, it was a big blunder. Okay. Does it make sense? Yeah. Okay, so now, so now what about the first term? Well, the first term is kind of, we're going to use a very naive bound on the first term.
So, Prasad, when you telescope, you still need minus d, minus some xt minus x star, right? Something.
Oh, the last term? Do you mean the last term?
Yeah, when you telescope, only the middle term should cancel, right?
I think, so basically the telescope is of the form d1 minus d2 plus d2 minus d3.
Yeah, so add those up and you're going to get d1 minus d3, right? You add the first two terms.
Right, you get dt minus dt plus 1. If you add them up, I'll get d1 minus dt plus 1. Yeah, that's right. Yeah, that's right. Actually, there is a final term.
But that's basically 0. So
that's basically 0, or in fact, it's sort of going in a direction which is good for us because it's negating us, right? It's going to be minus xt plus 1 minus x star whole squared, and I'm going to, since there's a less than equal to here, I'll just decide to drop that term.
Okay, sure.
Yeah, that's good. Good. Okay. So then, then we are just left with the first term. The first term, we're sort of going to use a naive bound. Well, what's a naive bound? We know that xi minus xi plus 1 minus xi is just eta times the gradient at f of xi. That's, of course, the definition of the algorithm. So we're talking about the norm squared of this guy. And of course, we assume that the function is Lipschitz. So meaning the gradient is never longer than L. So it is eta squared L squared. Okay, so you just use that bound here and you end up with eta squared. Let me just simplify instead of writing everything down. Okay, there was a 2 here, I think I missed. Yeah, but basically I get eta L squared over 2 times t plus r over 2 eta. Okay, where r was the distance between the first initial point and the optimum. Maybe I should have a square here to avoid this complication. Okay, so then you just solve for the best value of eta, right? You pick the best step size right now. Step size eta to be the one that minimizes this. So I think you pick r over L square root t. Actually, let me use r squared. R squared. Yeah, I think this is good. So then you get this to be RL over root t. Okay, that's it. So that's the theorem. So I mean you see that it's fairly symbolic. It isn't, but there are very few pieces of critical steps. I guess the most critical thing to remember is this fact that at any point the gradient is steeper than this value. Right? That's your certificate that you can make progress, and that's what we started with. That's our first step in this proof. Afterwards, there's a little bit of symbolic manipulation. Yeah. Any questions about this?
Professor, how do you get from the step where it says eta squared L squared to the next step. So the last two steps.
Here. Oh, this one. Oh, I substituted, right. I had this, I substitute this over here.
Oh, I see. Okay, thank you.
Professor, last week you said that this theorem only works for appropriate eta. Does that mean this specific R over L square root T?
Right. Yeah, that's right.
Is there like a bigger, possibility? Like
as in right. So this proof, as of now, I didn't use anything about the value of eta until the last step, right? Until the point I came here. So you can pick a different value of eta, then it'll still. I mean, you fix an eta, then you can find a t at which things will work, right? This is sort of if you want the best possible rate of convergence for a given t. If you fix a t and you want the best possible rate, you could do this. You could pick this eta, but alternately you can just fix an eta that you think is fine, and then you pick t large enough. This would still work. Sorry, I think I at the end I sort of skipped another step. So what we calculated here is the total error or total error across t steps, right? Or total regret, I guess. We'll come to this terminology later, but basically this total regret across t steps. And then of course the theorem was per iterate, what is the regret? You divide by t. So it's a 1 over t summation f of xi minus f of x star is eta L squared over 2t plus r squared over 2 eta t. Okay, so you see that you can fix any eta you want. When you make t sufficiently large, you're fine. And I think the best choice of eta for this particular analysis is to pick this, and you get 1 over square root t convergence.
Okay, thank you.
Well, Professor,
Mm-hmm.
when you do the average regret, I don't think there's a t in the denominator in the first term, because when you divide through, doesn't it go away?
Oh, in the second term, you mean? So this
On the right hand side, yeah.
Oh, over here.
Yeah, it says eta
Oh,
L
yes,
squared over
thank
2t.
you. Yeah,
but
yes, that's right. Yeah, thanks. All right. Anything else?
For a practical setting, we wouldn't know what R over L is, right?
Well, you would know, you would have some estimate on R and L.
Okay.
You'd have some estimate on R and L. And as we said, you fix any value of R, L, and eta. You get some bound, right? This proof still works, gives you some bound. The bound improves as t goes to infinity, but yeah. It doesn't go to 0, as was pointed out. This first term is independent of t. And that makes sense because if your function changes at at the rate of L, then you should know that, and you should take step sizes smaller than that. Like that's your margin of error. Like if you take steps of size eta, you'll incur error, which is eta L, effectively, right?
Professor?
Yes.
How do you get from the inequality from the second to last step to the equality in the last step? Should the last step have an inequality instead of an equality?
Thanks. Yeah, that's right. Yeah, it should be an equality. Yeah. Thanks. Yeah. Yeah. Sorry. Yeah. Okay. So this is that's right. Okay. So that's good. So we have a basic analysis of gradient descent. For different variants of gradient descent, you do sort of slightly modified versions of this analysis. So for example, this is kind of an important variant. Just to show you what is this important variant. Well, you want to minimize a convex function subject to the function, subject to the x being inside a convex set K. So there's a convex set K, and then xt is inside, and the iteration, the projected gradient descent iteration is you add eta times the gradient, you get yt. Yt plus 1. You get yt plus 1, which is outside, because this is after you add the gradient. And now to get the next iterate, you project back to the convex set, where projection back is just minimize the L2 distance. Find z in the convex set such that z minus yt plus 1, the L2 norm is minimized. The closest point in L2 distance inside the set. So that's your projection. Okay, so this is a slightly different variant. So each time you're going, adding the gradient and then projecting back to the convex set. So how do you analyze this? If essentially the proof is nearly the same, except for a small change. So let me try to show you that with a different color. All right, so this is the analysis of projected gradient descent. Well, again, you start with the same expression, and then instead of xt minus xt plus 1, you write down xt minus yt plus 1. Right, this is what, that's the only thing that changes. Okay, and then you apply law of cosine to what you have here. So you get xt minus yt plus 1 whole squared, right? Plus xt minus x star whole squared minus yt plus 1 minus x star whole squared. Okay, it's the same. It's just redoing the same thing with yt plus 1 instead of xt plus 1. Okay, and so then, the only trick is, again, the first term here, for xt minus yt plus 1 whole squared, you will use a naive bound, which is this is the gradient. This is the gradient. So you use the naive bound that this is at most L, just like we did here. The first term be bounded by L. The second term looks like it has this xt minus x star, but the third term, instead of being xt plus 1 minus x star, it's yt plus 1 minus x star. Okay, so you're not getting telescoping, but you're just one step away from telescoping. What do you use? You use the following fact about projections. So what's the fact about projections? If you have a convex set K, and then if you have a point outside Y, and you have a point inside X star, and you project Y to get to the convex set, you get pi of Y. So the projection is always closer than the original point. Okay, the projection of the point Y is closer to X star than Y is to X star. This is for all X star in the convex set, and then for all Y. Basically, it's just saying the projection always takes you closer. And so you just use that inequality here and you're done. Okay. You go back to the same proof. The rest is the same proof. Okay, so it's right. That's about all I wanted to say about the proof of gradient descent. Any questions on that? Okay, So, all right. So before we go on to mirror descent, some comments on gradient descent, which I think some of this we commented on last week, but just to make sure it's all there. So first thing to notice is the number of iterations is actually independent of dimension. That's kind of nice. So this method is in dimension independent. You can do it in n-dimensional space or in square dimensional space. All that matters is, or infinite dimensional space also, it doesn't matter. All that matters is that your distance to optimum is R, and you have a Lipschitz function of L. So for example, you could be doing gradient descent over the space of functions over the real line, which is an infinite dimensional space, and the same bound would hold. Okay, that's kind of that's very nice fact property to have. It's well, the convergence bound, we got order 1 over root t convergence, right? So order 1 over root t error in t iterations. So this is actually tight, as in this is optimal for Lipschitz functions. So note that the only thing we assumed about the function is that it's Lipschitz, and so it can be non-smooth, right? So so it need not have second derivatives. Of course, we assume that implicitly in our algorithm, we assume that it has first derivatives because we use the gradient of f in our algorithm. On the homework, there is a version of this where you use subgradients instead of gradients. So which means it doesn't even have to be differentiable at every point. But this is optimal. And note that this error is actually, it's fine, but it's actually pseudo polynomial time right? Meaning to get for error epsilon, you take order 1 over epsilon squared iterations, which is a little bit bad because if you want 2 to the minus b bits of precision, you don't want 2 to the minus b precision or b bits of 2 to the minus b error or b bits of precision, then you would need a runtime which is not 2 to the 4b or something, 2 to the 2b, right? It is exponential in the number of bits you need. So, okay, and what else? Well, the other thing is only thing we assumed is you can compute gradients, or actually, as you'll see in the homework, you just have to compute subgradients. So you just need a gradient oracle, right? You just need to be able to compute the gradient of the function to run the algorithm. And in many cases, you don't even need a gradient because even if you just have a value oracle, meaning you can just estimate the value of the function, you can estimate gradients easily if you can estimate the value of the function. Right, so I mean there are many estimators many ways to estimate the gradient. The most naive way is if you're at a point, sort of sample points in the tiny neighborhood around it, and then try to fit a linear function, right? That's like the most naive thing. But you can try more simpler, more succinctly clever things, like for example, if I pick a random delta, so like this is sort of an estimate of a gradient. Sorry. Well, basically all I mean is, okay, let me try to do it this way. So yeah, so f of x plus delta times delta, right? And you have to scale it appropriately. So Okay, if you like, this is basically in one dimensions. This is just saying I have to take f of x plus delta minus f of x minus delta and divide by 2 delta. Okay, in many dimensions is a version of this, but yeah, it's quite easy to estimate the gradient. And also you can even have a randomized estimate for the gradient. And that brings us to, I guess, what's one of the most widely used thing nowadays, which is the stochastic gradient descent. And in stochastic gradient descent, you don't have the gradient, but you have an estimator for the gradient. You have an estimator, let me call it E of x. So, well, E is probably a bad word, theta of x, such that the average value of that estimator is the gradient at f. Okay, so this is nice because you can basically, you can basically pretend that theta is a gradient, and you can just run the gradient descent algorithm. And if you look at the analysis of we just did, you can actually, if you go through it carefully, you'll see that the analysis interact nicely with this averaging. So although theta is only on average the gradient, the analysis works neatly with averaging. You can push the averaging inside the argument. So I mean, that sort of gives you like the basic analysis of stochastic gradient descent. Okay, and finally, this is sort of the worst possible situation you can be. You have a Lipschitz function which is non-smooth. Usually you're in much better situations. Your function is smooth, right? Meaning the gradients change slowly. That'll be, you can get 1 over t, or even better, sometimes you will be in a situation where you have a smooth, strongly convex function. If you have a smooth and strongly convex function, okay, so in this case, actually, you can get exponential convergence after t iterations. You can get exponential convergence. Smoothness parameter, and alpha is a strongly convex parameter. Strong convexity parameter. So, like alternately, if you know that the Hessian, the second derivative matrix of the function, the Hessian of the function has its smallest eigenvalue. So the smallest eigenvalue of the Hessian is at least alpha, and the largest eigenvalue of the Hessian is always at most beta. If you know this fact, then you can get a better analysis of the algorithm. You get an exponential convergence to the optimum. Okay, and this is usually what we mean by polynomial time algorithm. You want to compute b bits, you take poly in b time. This is really a truly polynomial time algorithm in some sense. And that would be the gold standard. So okay, any questions so far? Okay, that's good. All right. Oh, okay. So we are, I think we are halfway through it. So here's a plan. Let's just take a quick 5-minute break, and then we'll talk about mirror descent. And what I'll do as we take the break is I will create a bunch of breakout rooms, and I won't assign anyone to any room, but if you'd like to just go and chat, I'll just create a room, and I'll close out the rooms in 5 minutes. All right. Okay. And if you want to just hang out here and ask questions, that's also fine.
Professor, I had a quick question. So when you say polynomial time algorithm, do you mean in number of bits?
Yeah, that's what I mean. Yes.
Okay. Okay, cool. Thank you.
Yeah. Yeah. That's right. Yeah, I mean, that is actually sort of at the boundary of two areas. So the whole area of combinatorial optimization and minimum spanning trees and all the good old polynomial time algorithms is polynomial in the number of bits. And then there's a whole community which is numerical methods and so on, where this is not, super important.
Yeah, there's some.
It is clearly important to get exponential convergence, but it's sort of it's not clearly brought up. But yeah, it's important.
There's some cheating going on here, right? Because your arithmetic up till now needs to be of arbitrary precision, right?
Right. Mm-hmm. Mm-hmm.
And then you're saying, oh, I'm accurate up to b bits. So.
Oh, yes, yeah, you're right. So actually, yeah, there's a lot of cheating in that sense, but right in the sense of how accurate I am. Yeah, usually that is actually quite hairy to really work out. As in, if I did all these operations with finite precision, like b bits, if everything was finite bit precision b bits, yeah, how well does it work? It's quite hairy, yeah. But it's done. I mean, it's.
I guess, well, there's just addition and multiplication at b bits, right? So if your eta is like a power of 2, then probably not that bad.
Yeah, I think, but I guess really following through on the number of bits is quite annoying, actually. If you think about even solving linear systems, actually, that's annoying already there.
Yeah.
But I think if you go back and look at the first polynomial time algorithm for linear programming, right? So that's where actually I guess one place where this interface between the two communities comes up, right? So, well, linear programs were solved in practice since what, 40s or 50s, like whenever it was invented by simplex.
Yeah, echelon form, yeah.
Right. And the first polynomial time algorithm was Kachian in the late 80s or something, late 70s. And it's a big deal, right? The first polynomial time algorithm. But then if you try to say, okay, is it really polynomial time? Yeah. You try to look into that. There's a paper by Grotzel, Lowas, and I'm missing the third name, GLL, maybe Lenstra. Okay, basically 3 people who basically comprehensively worked out every bit calculation, what happens if you do it in this precision and so on. Yeah, you should look at, if you look at that paper, it's like so long, but it's, yeah, it's quite tedious actually to do it. But that is the sort of the reference.
Yeah, that's too much work. Please don't do that.
Oh, I mean, no, yeah, I guess we won't. Yeah.
So when they did the analysis, did it turn out to be polynomial in the number of bits?
Oh yeah, I mean, they have, I guess, I mean, it is polynomial in number of bits. You just have to be really formal about what we mean by being polynomial. For example, if I just say a linear program can be solved in polynomial time, that is a fair thing to say, because linear programs have a special property that if I give you a linear program where every coefficient is a b-bit integer, then the solution is also a rational number. So at least you don't need infinitely many bits to write down the solution exactly. So you can write it down in polynomial in fixed number of bits. And then the question is the number of bits you need, does it grow super polynomially as you do all these operations, right? Intermediate operations, you don't want it to grow. So yeah, you need to really work out to prove that if I give you a linear program with b-bit integers, you can write down a solution in poly in b time. Right, that is Yeah, that's a tricky theorem to completely work out. But yeah, if you go to other things like SDPs or semi-definite program, the true optimum cannot even be written out in finite number of bits, meaning it's not a rational number. So if it's not a rational number, then you really have to deal with accuracy. Here's a to get it in epsilon accuracy. Then yeah, it's a little bit iffy whether what's the right definition of efficient. But it is important to get exponential convergence, and they call it linear convergence. If I close out the breakout room. All right, so this is good. Oh, sorry. Okay. All right, so now we'll talk about mirror descent. Okay, so one thing that should really sort of make one uncomfortable if you stare closely at gradient descent is it's sort of a strange thing to do. I mean, geometrically it looks fine, but if you think about it.
Wait, could you share your screen?
Oh, I'm sorry. Yeah, this iPad. So it's a strange thing to do because geometrically it just looks like you're going in the direction of the gradient, but algebraically or in terms of units, it's a little bit off because you're taking a vector x, right, and you're adding the gradient to it, right? If just in terms of units, physics units, right, x and the gradient are not in the same units, right? X, right? It's a strange thing to just add the gradient. And this is more conceptually wrong if you think about mathematically where do these xt and gradient live. Okay, so where is xt? So let's call the space xt. That's the place where we optimize. Right? Xt lives in this space which is r to the n. Let's call that the primal. I mean, it is where xt lives, right? And if you have a space like that, the gradients live in the dual space. The gradients live in a dual space. So what I'm going to say now is not super important to follow what happens next, but if you look at function spaces or in functional analysis, you have, for example, like LP space. LP space is R to the n, where the geometry is the p norm geometry. P norm as in summation xi. The norm of a vector is the norm of a vector. Is summation xi to the p whole to the 1 over p. So L2 space is the most natural Euclidean space that we think about, but you can pick a different value of p. So if you pick L infinity or L1, right, these are all different spaces. Okay, and if you have your vectors x living in LP space, the gradients naturally live in LQ space, which is also, which is basically R to the n, where the norm is the Q norm. Okay, and they're the Q norm, and such that Q 1 over Q plus 1 over P is 1. It's the dual space. Alternately, another way to say, actually, formally in function analysis, the easiest way to say what these are is the following. Well, x is just a vector, right? X is just a vector. Okay. What is if you think about it in terms of types, what is the type of the gradient? What's the type? Well, if a gradient is something which, if you give it a vector, it'll give you a number. Gradient is basically the type of a gradient is it's a function that takes vectors and gives you a number. It's a linear functional. So in some sense, it's of a different type. It's an object of different type. It lives in a different space, which is the dual space, and it's an object of a different type. Like why is a gradient a type which takes a vector and spits out a real number? Well, what is a gradient? Gradient is something like what is differentiation of gradient let you do? You're at a point. If I tell you some direction to go, the gradient tells you how steep it is in that direction. Right? It's a so that's why just adding the gradient to this is not the most obvious or natural operation. And in fact, there is no natural single operation that you can do with the gradient. You can use the gradient in different ways than just adding it. And that's what we'll see. So it doesn't matter if this discussion didn't make so much sense. I was just trying to, for people who have seen a little bit of functional analysis or LP, LQ spaces, just to point, I was just trying to show it to you there. But basically, something is odd with the gradient and gradient descent algorithm. The types don't match. So here's a different version of gradient descent with a different way to state gradient descent, which actually makes more sense. So this is called, I guess, proximal gradient descent. So what's this version? So the idea is, of course, you have a starting point, right? X1 is a starting point. And your new, so how do you calculate the new iterate? Well, okay, you are at xt, right? You're at xt. Okay. And around xt, you have an approximation to the function, a linear approximation to the function, right? Sorry, you have a linear approximation to the function around xt. Well, what is the linear approximation? It is just the gradient of f of xt times x minus, let me use y. Let me use x, let me just use x minus xt plus f of xt. Okay, so this is a linear approximation. Let me call this function cap h of x. Right. So this is just a linear approximation to the function around xt. That's how the function looks like around xt. So you could say, let's just minimize this linear function. Okay, that's a natural thing. But then, that this approximation, linear approximation, is going to fail if you go a little bit far away from xt. You don't want to go too far away from xt. So what you do is you write down a different, you say minimize the linear approximation, which is eta times okay, minimize the linear approximation, but you add a penalty for going too far. So you say so you had a penalty, which is in this case the 2 norms squared for going too far. So you say your next point is the minimum value or the point that minimizes the following function. Okay, so that is really so it's an algorithm. It's a definition of an algorithm. At any point, take your linear approximation, add a penalty for going far away, which is this quadratic penalty, and you minimize this quadratic function now. And you go to the minimum of this, that's your next point, and so on. so each step of this iteration is actually minimizing a quadratic function, right? That's what you're doing in each step. Right. So so note that the way I wrote it, this linear function looks different than the linear approximation here. But I have basically dropped terms which don't depend on x, right? Drop terms that don't depend on x. Because you're anyway minimizing over x. So whether you minimize like this linear approximation or this simplified one, it's the same. So for example, I'm as well write minimize h of x plus the quadratic loss. It's the same thing. So that's why it like finding the point that minimizes h of x plus the quadratic loss is the same as a point that minimizes this thing that I wrote here. Okay, so does that make sense? So that is really okay. And actually, this is a different way to look at gradient descent. In fact, let's just work that out. Well, okay, at each step I asked the algorithm to minimize this, right? To minimize this function, which is eta times the gradient f of xt in a product x plus half norm x minus xt whole squared. Okay, so I asked the algorithm to minimize this, right? That's how I get xt plus 1. Okay, so it's a quadratic, so you can do the minimum. You can find out the minimum just by calculus, right? You can, if I call this h of x, let me call this just to avoid confusion. Let me call this g of x. Okay, I mean, how do I minimize it? Well, I take the gradient of g of x and set it to 0, right? This is a standard calculus. You want to find the minimum of a quadratic or any function. If you want to find a stationary point, you just set the gradient to 0. So if I want to set the gradient to 0, what is the gradient? Gradient is gradient with respect to x, of course. Xt is fixed. X is our variable. So, well, there's the linear term that just gives you eta gradient f of xt. Okay, and then the quadratic term gives you, let me write it this way, half 2 x minus xt. Okay, this is just differentiating. I'm just differentiating g of x with respect to x and seeing what I get. And you can see that this is the same as saying my x is actually xt minus eta times the gradient of f of xt. Okay, you see that we essentially recovered the gradient descent update rule, but in a somewhat more natural way. Now I'm not just adding the gradient, I'm just saying minimize this linear approximation with a penalty added in. So the definition doesn't go through dual space as of now, the definition of the algorithm. Does it make sense? So it's just a reformulation of gradient descent. Okay, that's good. So, but what it opens up is, now it opens up the possibility that I don't have to add a penalty, which is a quadratic penalty. I can think of adding any penalty that sort of prevents me from moving away from xt too much, right? And depending on what function I pick, what function I add as this regularizer, this is a regularizer. Depending on what regularizer I use, I will get a different algorithm. right? And essentially you can imagine putting down any regularizer, any regularizer, but there are some properties of the function that you want to put there, which will actually make the analysis simpler, right? Which will help you analyze. So that's what we'll do. So
Actually, Prasad, can I ask one more question?
yes.
So the fact that this regularizer is like is a quadratic term in the distance is what makes it kind of complicated, right? If it wasn't a quadratic term and if it was linear, then you can do this. This sort of looks like expert's algorithm, right? You just update each. If you look at this with like each component of the vector x, if you just have the inner product term, then it's pretty easy to update each xi, right? The non-trivial term comes from this regularizer.
Right. So actually, we like, I guess with regards to experts, we'll see that you put a different regularizer, which is the KL divergence. You will recover the expert's algorithm. So different choices of regularizers you put there gives you different, algorithms, and they're sort of suitable for different. I want to say they're suitable for different geometries of the problem.
No, my point more is that this arg minimizing seems like you can do it really well per coordinate, right? Except for this last term.
Right. Yeah. No. So the usually. So usually what you do is you pick a regularizer. We'll pick a penalty function for which this argmin is actually easy to compute. As in all the cases that we'll see, or in all the special cases of the algorithm that we'll see, we'll actually be putting in some regularizer, like the quadratic or whatever exponential or whatever regularizer we'll put in. This update would by itself would be easy to compute. And so for the quadratic update, you see that we recovered, the good old gradient descent, right? And that is very easy. We just have to add the gradient, right? Just have to add eta times the gradient. So we recovered basically our simplest algorithm. It just looks more complicated, but for different, in all the cases we'll actually pick fairly natural regularizers. So actually, let me. So I think
right. Yeah. You in this case you get the coordinate by coordinate update.
Yeah.
But that seems like a huge bonus for choosing this quadratic regularizer. That's what I'm trying to say.
Right. No. Yeah. So you do get actually in right. We try to keep the regularizer. Usually, many algorithms try to keep the regularizer simple here, so that they keep the regularizer simple so that the algorithm each step is simple. Yeah. I mean, also, I think, right. Here's just a general comment on this sort of work, right? So note that all of the things that I'm describing, mirror descent and gradient descent and everything, this comes from literature which is like from the 80s or 90s, from optimization, right? Like people like Nemirovsky and so on. And in that world of algorithms, the description of the algorithm and the algorithm itself are usually extremely simple, right? As you see, gradient descent is just add the gradient, and the mirror descent in all the standard versions of mirror descent is just, just, do the most natural, simple thing. So as in the algorithms are very simple to state. And I guess, you could say that, like when you try to design algorithms for combinatorial problems, you can try to venture out to doing things which are more complicated for the particular application at hand, right? So for example, if you have graphs, right, maybe you should pick a regularizer which depends on the graph, like which is some function on the graph, right? So that's more, right? We're getting, right? That's sort of, yeah, that's where like our world meets here. Yeah. Right. So okay. So what sort of like what's the broad setup for this kind of a thing? This is called a mirror descent. So the basic function that that you use to substitute for a quadratic is a Bregman divergence. So what's a Bregman divergence? You know, to let you pick a convex function, a strictly convex function, strictly, or you could even say strongly convex. But basically, a strictly convex function is, as you can imagine, it's a function that is never flat. It always is moving. There's no section of it which is flat, right? It's never a linear function. Right? It's always, there's a little bit of tilt upwards at every point, right? That's it's never flat. Okay, so okay, so what's if you give me any strictly convex function on some set, let me just say R to the n for now. Okay, you have a strictly convex function, H. So how do you define Bregman divergence? So you can associate a Bregman divergence with it, d sub h. Okay, what is d sub h? It's like a distance function, right? It's you want to calculate the distance of y from x. Okay, so what is the distance of y from x? Let me see if I can reproduce this picture. I think if you just remember this picture, sort of is good. So this is our function h. Okay, and you're at a point x. Okay, and there is a linear approximation to the function at x. Okay. There's a linear approximation to the function at x. And of course, your h will stay above this linear approximation. It's on top of this. And if you give me any other point y, let's say this is y. Okay. And so this is h of y. And you see how much above the linear approximation h of y gets. So this distance between the linear approximation and your curve, that is the Bregman divergence. That is the divergence d sub h of y from x. Right, so clearly what is it? Well, it is just, you take the function at y and see how much above the linear approximation it is. H of y minus h of x plus gradient h of x in a product y minus x. Okay, so that is a Bregman divergence. And you can see that it's for a convex function, as you move away from x, intuitively the divergence goes up, right? So it does seem like a penalty that you incur. Like it looks like a penalty function that is keeps you close to x if you add it. It grows as you go away from x, and so that's the definition of a Bregman divergence. You pick any convex function, you can write down a corresponding Bregman divergence. Okay, so right. So here are a couple of examples. Right, so if I pick my convex function to be just the 2 norm, then as you can imagine, the Bregman divergence nicely turns out to be, I mean, it's a good exercise to work it out, but it nicely turns out to be the distance squared. Right, so this recovers our So a gradient descent, the vanilla gradient descent starts with the convex function, which is the 2 norm, and you can write down its corresponding Bregman divergence, and you get the thing. And okay, what else can you use? Well, if you use this function, which is okay, this is it's the normalized entropy of a probability distribution. But basically, for now, just think of it as a function or positive real numbers. Right? This is a function defined on, because I'm taking ln in over here, it's a function that defined on r plus to the n. Okay. And then the corresponding Bregman divergence is something that we sort of must have seen in some context, which is the KL divergence, which is like the KL divergence between the probability distribution y and the probability distribution x. It is sum over I yi ln yi by xi. Okay, so that's good. So now you can just use this back in the definition of the algorithm here. What you recover is the multiplicative weights algorithm, the multiplicative weights of the experts algorithm. You get that by just using this as your regularizer. Okay, and you can use instead of k, we use the version of entropy for probability distributions. Instead, if you use the version of entropy for PSD matrices, you get this algorithm called the matrix multiplicative weights, if you have heard about it. But basically, you can, by just using a different choice of this H, you recover different algorithms. And so all of them are doing just this thing. And actually, let's do one example, which is kind of nice. It sort of goes back to our thing earlier. So let's say I use h of x to be, instead of the, so earlier we had the quadratic, right? It was x, right? This is what gives you gradient descent. So instead of this, if I use h of x to be x, some other matrix, let me call it A x, okay, where A is a PSD matrix. So, I mean, if you want to think about it, instead of summation xi squared, let's say I use summation wi xi squared for some wi greater than or equal to 0, right? Basically, it's you can use any quadratic, positive semi-definite quadratic as my convex function. All of them are convex functions. So I can start the whole Bregman divergence business with that convex function, right? And then I will get, what do I get? I'll get the update, which looks like, I'm going to write down the update. I'll leave it as an exercise to work this out. It basically, if you use h as this function, h of x is x transpose ax, if you use that, and you construct the Bregman divergence dh, and then you use that in the algorithm as a penalty, then you'll recover an update that looks like xt plus 1 is xt minus a inverse gradient f at xt. So, I mean, I guess the only thing I want to sort of emphasize here is that what happens if you just use something like something like this, where you change your penalty. You change your penalty, right, from summation xi squared. That was your original penalty for moving away from the function. Now it's a different penalty, which is summation wi xi squared. It's sort of a penalty weighs different directions differently. Some directions the penalty doesn't grow quickly. Some directions the penalty grows quickly, depending on the values of this wi's, or depending on how this quadratic function behaves. So this gives you what we were referring to last time. This is basically preconditioned gradient descent. So in the last class, towards the end, we were talking about this issue that if you have a contour which is very steep along one direction and very flat along another direction, you would want to adjust your gradient descent to sort of take into account this, meaning it can take long steps in the direction where it's flat and very narrow steps in the direction where it is steep, right? Basically, in our gradient descent analysis, there's a single eta, which is a step size. Effectively, what you want to have is two different etas, right? Like it should be moving faster on the direction where it's flat and slower on the direction where it's steep. So how do you achieve this? Well, you can, if you knew that the geometry looks like this, and if you knew the A corresponding to that, as in the quadratic form that forms these contours, then you could use that as your, H or the Bregman divergence, or you could write down the corresponding preconditioned gradient descent, and that will work. That will just, that will work faster, meaning it will give you exponential convergence where only you didn't have that, right? So that's the, so basically by this proximal gradient descent, instead of picking the two norm quadratic norm, because you're picking a Bregman divergence here, right? You're allowed to pick a very strange looking penalty function. You're allowed to, it lets you exploit your knowledge of the geometry of the situation. It lets you change the geometry, right? Using the two norm is like saying, I have the same penalty whichever way I go, my penalty is how far you went. That is a two norm. But if you know something about the geometry of the problem, you should use it. So meaning, for example, for probability distribution, it turns out that this function is especially nice. And that's why multiplicative weights have much better performance than just good old gradient descent when you're dealing with probability distributions. When you're dealing with probability distribution, the space you're working on is a space of probability distributions. The space of probability distributions is the geometry is the L1 geometry. The geometry is, or actually not the L1, the natural geometry is the KL divergence geometry, right? So the most natural geometry for probability distribution is the one given by KL divergence. So if you use this as your strongly convex function, you get the right algorithm, which is the multiplicative weights. For vanilla gradient descent in Euclidean space, the geometry is given by this thing, right? You can be super aggressive and say the following: I don't care, I don't know what this domain is. At every point, I will look at the function and choose the geometry, right? That could be an algorithm. That corresponds to using a regularizer, which depends on the function. So if I did xt plus 1 is argmin over x of the linear part, which is gradient f of xt inner product x. Okay, and then the penalty, what penalty do I use here? Well, I'm going to use a quadratic. The quadratic I will use is x transpose h of xt x. So just to write it down, h of xt is the local Hessian of the function. H sub f is a Hessian of the function, meaning it's it's a second derivative matrix. You have a convex function. Locally you have a Hessian, which is a PSD matrix, right? So you can say, okay, that's my local geometry of my domain. So I'll just use directly that as my penalty. So this looks very nice. Unfortunately, this is much harder to analyze, but this is what is called the Newton method. So the Newton method is essentially this. You could say it's proximal gradient descent, where the penalty is given by the function itself. But there's another simpler way to say the whole thing. If I look at the first, if I look at these two terms together, that is the first two terms of the Taylor series expansion of the function f. It's the quadratic approximation of the function f. Right? Because the first term was, of course, the linear approximation. And then what I did was the second term also I picked from the function itself. So I got the quadratic approximation to the function. So minimizing that is the Newton method. So actually, I think I got this wrong here. Let me write as x minus xt, x minus xt. Sorry. So, it should be like the quadratic that I use there is x minus xt transpose h sub f at xt, x minus xt. Okay, that's the penalty to use. So,
Professor, should there be a factor of 1/2?
Sorry?
Should there be a factor of 1/2 in the quadratic term?
Oh, yes, there should be a factor of 1/2. Yeah, actually, there's also, you could also use an eta here, right? Like in our original yeah. But there should be a factor of 1/2 that will be the quadratic approximation to the function. Yeah. So Newton method is there's a factor of 1/2, and you have this. Right. But this turns out to have very, very good convergence. So the convergence of the Newton method is even faster than our strong convexity gradient descent. So the convergence is log 1/epsilon. So to get epsilon accuracy, you just need log 1/epsilon iterations. It's very nice, but you can only prove this convergence under a sufficiently nice neighborhood. If you start at a sufficiently nice neighborhood, so it's But you see that all of the algorithms sort of are kind of special cases of this broad phenomena, which is you take the linear approximation and you add a penalty, and you change the penalty, you get different things. Okay, I think I should stop here. Any questions?
I had one question. So is it possible to, instead of using the quadratic approximation, use the third order approximation?
So I think I haven't seen an algorithm that does that, but I think the real issue, one real issue with that is if I give you a degree 3 function, it's difficult to optimize it. There's no easy way to optimize a degree 3 function. In fact, it'll become NP hard in general for a degree 3 function. But for a quadratic function, you can essentially explicitly write down the optimum of a quadratic. That's how we proved the gradient descent update and so on. By just differentiating, setting the derivative to 0, you can basically explicitly write down the optimum for a quadratic function, and that's the reason why you wouldn't use the cubic unless you know something about the cubic. Anything else?
So when you try to minimize a cubic, you get a system of quadratics, right?
Right. Yeah.
So does that turn out to be NP hard?
Yeah, I think so. It's difficult to minimize a cubic. Yeah, if you have a system of quadratics, yeah, it's difficult to do that. Yeah.
Are there numerical methods for solving systems of quadratics?
Not in general. Like there's no, all the algorithms that we're seeing are provable. There's no provable way to minimize a cubic. Right. And it sort of makes sense. Like even when I say minimize a quadratic, we are actually implicitly making sure that our quadratic is a convex function because we're picking a PSD thing. So really, at least the sub problems in every step is still a convex minimization. But if I just use the first three terms, then I get a cubic, and it might be completely non-convex cubic, right? It's the first three terms of a convex function need not be convex, right? The Taylor series approximation. So you could have lots of local minima, and we don't know actually. The terrain can be crazy looking.
I have a question. It's somewhat unrelated to like our discussion of proximal gradient descent, and more regarding when you said there are issues with adding the gradient to your vector because it's a dual vector.
Right.
Now, like if I remember differential geometry correctly, then isn't it the inner product with the gradient, if you view that as a linear functional, that's the dual vector and not the gradient itself? So
Right.
why can't, what's the issue with adding the gradient there?
Right. So when you write down gradient as a vector, right? So gradient is a vector. At first, at the most basic level, gradient is a linear functional that given a direction tells you the steepness. This is the type of a gradient. But you can also express it as a vector itself. You can write down the gradient like the way you calculate, since it's a linear functional, you can also write it as a gradient of f of x in a product y, right? This gradient of f of x at y, along y, is gradient of f of x in a product y, right? But if you write down a linear functional as a vector, that vector lives in the dual space, meaning its geometry is in the dual space. So I guess if you work with Euclidean space, like the geometry is the same. L2 and L2 are dual or self-dual of each other. But I think a good example is maybe if you work with let's say you work with L1, right? Okay, in L1 here, then this will be L infinity. What that means is, if I look at the unit ball in the X space, the unit ball in the X space looks like this. This is an L1 unit ball in, let's say, even in 2 dimensions. In 2 dimensions, the L1 unit ball looks like this. The L infinity unit ball looks like this. So the geometry of X, this is where, like, this is the geometry of X, and this is the geometry for the gradient vector. Like, that's the natural geometry for the gradient vector, right? So like the gradient vector, its normalization is it's like the distance for the, like its normalization is in the dual norm. So
I guess I'm wondering then why the dual space naturally inherits the dual norm, because it's the dual space in itself, you can put whatever inner product you want on it, right? So
right, why does it naturally inherit the dual norm? Well, even before, right? So like even before you draw a picture to the picture that you associate with the dual space, if you just define it formally as the object that takes a vector and outputs a real number as a linear functional. Sorry, if you define the dual space as a linear functional, right? The natural norm on the linear functional is to say the norm of a linear functional, let's say it's in the dual space, sorry, is the norm is you take a unit vector in your original space, let me call that, it's a unit vector, and you ask what is the value that your linear functional outputs on this vector. Okay, so this is a natural norm that you can define on the, right, a norm of a function, right? The norm of a function, norm of a functional is the largest value it outputs on a given point inside the unit ball, right? The largest value it takes inside input. This is a natural norm I can define on the dual space of any function space, even without explicitly thinking of the dual space as a vector. Even if I think of it as just a function, this is a natural norm there. And you see that this norm becomes the dual norm. Like if you try to write this as an inner product, like if I replace this by, okay, there's a vector that I associate with this. If I write this, then this becomes the LQ norm of the vector, where 1 over p plus 1 over q is 1.
Okay. Okay. Yeah, that makes sense. So you're looking at the operator norm of the gradient.
Right. Right.
Okay.
Yeah.
Thank you.
Yeah. So yeah, basically the natural geometry in the dual space is the dual norm. Yeah. Nothing else. And actually these things become, I mean, for us, we're always in finite dimensional spaces. So things are okay, whatever, right? P norm, Q norm. It's sort of, I mean, usually you sort of push this under the rug, but I think if you work on real function spaces, there can be functions which have a finite LQ norm, right? But they might not even have a bounded LP norm, right? Like, right? So if and like, like the norm could be infinity in, right? So
right.
So yeah, these things become more important there. Yeah. Yeah, I mean, also all our algorithms, the gradient descent algorithms, they use, they are dimension independent, as we talked about earlier. So I'm sure there are applications of gradient descent which are completely infinite dimensional. And I'm sure they're there somewhere. If you find one, or let me know. And I was looking for a nice application which is completely infinite dimensional, which uses the fact that the analysis is actually independent of the dimension. Yeah, I couldn't explicitly find one. Anything else? Okay. All right. Yeah. Thanks. See you on Wednesday. We'll finish the proof of mirror descent and we'll go to online optimization.
Thank you.